Hello everyone, my name is Mariam Khorasanian and today I will be presenting my final project for mechatronics course supervised by Dr. Saeed Khan Kalamtari. The title of my work is Multitask Facial Emotion Recognition based on continuous dimensional space and discrete labels. This project is a full reproduction and critical analysis of a recently published multitask emotion recognition framework. Here is how I will structure the talk. I will start with the motivation behind the problem, then introduce the reference paper this work is based on. After that, I will walk through the architecture and method, explain the consistency loss that ties everything together, describe my experimental setup, present the results and comparisons against the original paper, show a qualitative real-world evaluation, and finish with key findings and a conclusion. Emotion recognition is a core capability for human-computer interaction, healthcare monitoring, driver safety systems, and smart education platforms. But there are two competing ways to represent emotion computationally. The first is a discrete approach. It has seven basic categories like happy, sad, angry, and so on. The second is the continuous approach, using the valence arousal dominance or VAD space, which represents emotion as a point in a continuous three-dimensional space. Most existing multitask systems compute these two representations independently, which ignores the psychological reality that they should actually agree with each other. This independence creates a real problem. If the discrete branch predicts happy, but the continuous branch predicts a negative balance score, meaning unhappy, you get a logical contradiction. The network is essentially disagreeing with itself. This is not just an aesthetic issue, it signals that the two branches aren't learning a shared, coherent representation of emotion. This is exactly why a consistency loss function becomes mathematically necessary to bind the two output spaces together. My work is based on the paper by Hu and Yi, Multitask Emotion Recognition Based on Dimensional Model and Category Label, published in IEEE Access in 2024. Their core approach is joint multitask learning, combining discrete classification with continuous VAD regression, implemented using four separate ResNet 18 networks, all bound together by a logical consistency constraint. My research objective was to fully reproduce their method and perform a critical code-level analysis of their official open-source implementation. Not just re-implement what the paper describes, but actually verify it against their real code. The model structure uses four parallel ResNet 18 branches, all processing 48 by 48 pixel grayscale inputs. One branch handles the 7-class emotion classification, and the other three each regress one of the VAD dimensions: valence, arousal, and dominance. I made a couple of customizations to match the author's actual implementation. A modified first convolution layer without max pooling, and proper single-channel tensor processing throughout the pipeline, since these inputs are grayscale, not RGB. The total loss function combines five terms: classification loss, the three regression losses for valence, arousal, and dominance, and a weighted consistency loss controlled by a lambda parameter. The consistency constraint is built from Table 1, which defines the expected sign, positive, negative, or near zero. of each VAD dimension for each of the seven emotions. For example, happy should have positive valence, arousal, and dominance, while sad should have negative valence and arousal. During my code level review, I found and corrected two genuine errors in the original equations. Equation 9 was missing the fear class under the arousal penalty term, and equation 13 mishandled the dominant sign rules for angry and sad. I fixed both to be fully consistent with Table 1. For experiments, I tested 8 configurations in total, 4 task scenarios, each run both with and without the consistency loss. These scenarios focus respectively on balance, arousal, dominance, and full VAD integration. I used a VAD annotated FER 2013 dataset containing 28,676 images. Training was done on Kaggle using two T4 GPUs for a total of about 7.5 hours across all experiments. Each run used 20 Apex SGD optimizer with a learning rate of 0.01 and a consistency loss weight lambda of zero point 0.1. An important part of this project was being honest about where my implementation deviates from the original paper and why. I made a deliberate choice. Wherever the paper's written text disagreed with the author's actual release code, I matched the code, not the text. For example, the paper claims 120 training epochs, but the actual code has 20 hard-coded, so I used 20. The paper doesn't specify batch size, but the code uses 16. I used 64 instead, due to the time and compute constraints. And the paper describes a learning rate decay after epoch 80. But since the real code never runs past 20 epochs, that decay never actually triggers. So I used a flat learning rate of 0.01, matching what the author's code actually does in practice. Starting with the classification results, my implementation achieved an accuracy range of 47 to 52%, which falls entirely within the paper's reported range of 45 to 55%. This confirms a successful reproduction of the core classification results. For the VAD regression results, 4 out of 6 comparisons match the paper's claimed direction. Specifically, all three public test cases, plus the dominance dimension on both test sets. However, my absolute regression loss values were 15 to 40 times higher than what the paper reports across all three VAD dimensions. I traced this discrepancy to the batch size difference using 64 instead of the paper's 16 results in roughly 4 times fewer gradient updates per epoch, which meaningfully affects convergence for regression tasks in particular. It was noting that adding the consistency loss did reduce dominance regression error by about 14%, which supports the effectiveness of the consistency constraint. Looking at the confusion matrix in more detail, the model performs very well on happy, neutral, and surprise, with 73, 62, and 65% accuracy respectively. But disgust is a clear failure mode at only 4% accuracy, frequently confused with angry or happy. This is primarily driven by extreme class imbalance in the FER 2013 dataset, where disgust has very few training examples compared to the other classes. go beyond the benchmark dataset, I also tested the model on real world photos sourced from Google search. An angry woman, a surprised woman, and a happy man. In all three cases, the classification was correct. But when I checked VAD sign consistency, I found something interesting. The angry and surprised examples were fully or mostly consistent with their expected VAD signs, but the happy man's case showed a valence sign mismatch. The model predicted happy but with a negative valence value, which shouldn't happen. This leads to my key findings. First, the equation corrections. Fixing equation 9 and equation 13 to properly align with table 1. Second, through independent literature review of concurrent VADNet research, I confirmed that dominance is the hardest VAD dimension to predict, a finding consistent across multiple papers, not just this one. And third, and I think this is the most important discovery, I found that the consistency loss implementation uses detach function on the classification output before comparing it to the regression output. This unintentionally blocks gradient flow back into the regression branches during back propagation. This directly explains the real photo valence sign failure I showed on the previous slide. The consistency loss isn't actually correcting the regression branch as intended because gradients simply can flow through the detached tensor. Based on these findings, I propose the three directions for future work. First, integrating or orthogonal regularization between feature dimensions, following recommendations from the author's or own follow-up VADNet paper. Second, removing the detach function call from the consistency loss so gradients can properly flow into the regression branches, directly addressing the bug I identified. And third, adding an automated face detection and corrupting pre-processing step, which should improve robustness on unconstrained real-world photos like the ones I used. To conclude, this project successfully reproduced the core findings of the reference paper. I identified and corrected two genuine errors in its published equations and extended the analysis beyond the original scope through qualitative real-world testing and independently sourced follow-up literature. I believe this kind of rigorous code level reproduction, not just rereading the paper, but actually verifying it against the author's real implementation, is essential for building trust in published machine learning results. Here are my references, and thank you for your attention.